In this video, we go through the derivations for kinematics equations 1 and 2. There are two other equations, and we'll derive those in another video. These are the four kinematics equations that can be used only when there is constant acceleration. If there's not constant acceleration, we can't use these. But in many cases, the acceleration is constant, and so these are great to use. Now, where do these come from? What we're showing here is constant acceleration motion. And what feature of this graph indicates uniform, that is constant acceleration? Well, that would be the constant slope. In other words, the slope is equal to the acceleration. Whatever the slope is, that's the acceleration. Let's use slope-intercept form, which you learned in your math classes, to derive equation 1. And I've reprinted equation 1 here. So this is the answer that we need to end up getting. And let's see if we can do that. Slope-intercept form is y is equal to mx plus b. What did we say just a second ago? That the slope was the acceleration. And x and y can be any points on here. How about we use this point right here? So the x coordinate is t. So let me put t in for x right there. And y is vf. And b is the intercept. Oh, well, that's v naught, isn't it? And what does this give us? This gives us vf is equal to, if I put v naught first, plus at. Look at that. Perfect. Sometimes people will write v sub I here for initial velocity, but in upper level physics classes, usually initial is indicated by this naught symbol. Question C, what quantity is represented by the shaded area under the graph? This is going to have the unit of, let's see, the vertical unit would be meters per second, and the horizontal unit would be seconds. And when you're finding area, you'd have to multiply those. So that would be meters. And what do we measure in meters? Displacement, for one thing. So I've recopied the graph here so we can continue looking at it. For the trapezoid shown in the graph, the area can be found by taking the what of the lengths of the parallel edges. Well, that would be the average, wouldn't it? Hopefully you learned that in your math class. When you're finding a trapezoid's area, you can take the two edges that are parallel and find their average, and then multiplying by the trapezoid's width. Let's see if we can do that to find the equation number 2 here, which again should be that. So let's find the area here. What's the area? The area is displacement. And what does it equal? It equals the average of the parallel sides. So that's 1/2. And what's the length of this parallel side? Oh, it's VF. And this is V naught. So VF plus V naught. There's the average of the parallel sides. And then we multiply by the width, which is an x coordinate of t. And this is an x coordinate of 0. So that's just t. Look at that. All done. Perfect. That's pretty neat. Now, why would I use one of these equations over the other? Well, you know, sometimes you're given the acceleration. Can I get both of these on the screen? Oh, look at that. Sometimes you're given the acceleration. Sometimes, you know, you might not be. Sometimes you're looking for displacement down here on the bottom. And this equation up here isn't going to be too helpful for finding displacement, just using it as it is. So if you know you have constant acceleration, you have a couple of equations to choose from that can help you find what you want. And we just derived the first two of those.